Hello, everybody. My name is Leo Yaffe. I'm co-founder, managing director of Jelurida, companies that develop the Ardor and the Ignis and NXT blockchain solutions. I'm here. Our product is a blockchain product developed in pure Java, running using normal JRE. And I would like to show you, today, I will show you how this a little bit how this product works, and I will demonstrate our contracts framework and talk about interesting challenges that we had to solve, how we tackled them. Hopefully I will be able to show you some demos as well. Okay, so let's start, but I assume that some of you are not familiar with blockchain, so maybe let's start with a few minutes, talk a little bit about what is a blockchain, what is this thing all about, right? So let's say that I have an apple, all right? And I hold my apple in my hand, I give the apple to you, so now you have one apple, I have 0 apples, the apple is visible, it's very easy to see it. But what if this apple is digital apple, some kind of MP3 file or a movie or something like this? I can send it to him, but I can also keep a copy to myself, or I can also upload it to Facebook and 1 million people will actually download it. So tracking digital content is much more difficult than tracking physical content. So what we usually do is we maintain a ledger. Okay, what does it mean, a ledger? I gave you the apple, so there is already a transaction that passes it, so I can't give the apple to you because this will be double spend, all right? So we want to prevent it. So we just maintain a ledger that looks like a book of accounting book. But then there's a question, who holds this accounting book? Usually who manages this on the internet? Either some large internet firms, the Google's, Amazon, Microsoft, also government office, or some clearing house or lawyer or something like this. And this third party charges fees or makes censorship or just has no motivation to do efficient work and so on. And we see it in our daily life quite a lot. So what the blockchain idea actually says that instead of one large entity that manages the ledger, everybody together will manage a ledger using open source product that anyone can actually review the code and make sure there is no backdoors. So you build a network of possibly thousands of nodes, each one without any connection to the other, but all based on the same protocol, on the same source code, and this network together decides what is the correct order of transactions in order to prevent double spend. So again, now let's talk, let's call this network Bitcoin, okay? And let's call this transaction sending Bitcoin from account to account. Then if I send the Bitcoins once, I cannot send the same Bitcoins to another address because this will be double spend, and the network together will reach a consensus which of the transactions is legal and which is illegal, right? So that's in essence what we are talking about with a blockchain. So it's a network that manages a decentralized ledger of transactions. So let's just review the general entities that participate. So transactions is a basic action in the network. It can be about sending tokens from address to address, but it can also represent a vote or registration of identity on the blockchain, or almost anything that you actually want to deploy to this decentralized blockchain. Then transactions are packaged into blocks. Block is actually a container of multiple transactions. Blocks are also the synchronization point for the network. The network what the network does is each each transaction submitted to the network start to propagate between the nodes of the network. At some point, one of the nodes in the network generates a block and broadcasts it to the rest of the network. Every node that receives a block revalidates all the transactions. So everything is completely copied to between all the nodes, and every node revalidates everything when it receives it. So if a node receives a block, checks everything that everything is correct, it adds a block on top of what it already has. So a block is always attached to the previous block using digital signature. So the digital signature of a new block contains a hash of the previous block, so that you cannot set them apart. And nodes build the blocks one on top of each other to form what we call a block chain, right? So, right, then just a little thing that how do we actually reach consensus? At the top of the blockchain, blockchains typically look like a one chain, but at the top of the chain there could be discrepancies because possibly someone is trying to double spend, right? And when I try to double spend, I can send one transaction to a node in China and another one to a node in Spain. So each node alone cannot tell that there is a double spend. But eventually, there could be two different blocks, one containing my transaction to China, the other containing the transaction to Spain. And these blocks by themselves could be legal, but only when merged together, they form a double spend. So the network has a way to identify that two blocks are conflicting, and then decide which block is stronger, and it will be added to the blockchain, and which block has to be disassembled, and all the transactions on this block will go back to propagate through the network until they really find their own block. If there is a conflicting transaction, it will eventually expire. So we are not going to punish whoever tried to double spend, but he will simply won't be able to do it. So now we have transactions, which are the basic actions, blocks, which are containers of transactions, and nodes that build these blockchains one on top of each other. Then there is accounts and addresses. So typically you have each user of the network needs to have a private key, okay? Private key and public key pair. Usually the address is derived from the public key, and it's a unique identifier of an account on the blockchain. When you send a transaction, you sign it with your private key, but you only expose to the blockchain your public key. This is, if you think in the context of payment, this is an advantage, for example, over credit cards. Because when you pay with a credit card over the internet, you expose your private key, or almost the private key in most cases, while in a blockchain context, you never expose your private key to the network. You only expose your address, which is based on your public key, which does not allow users to just take it and reuse it for their own, to sign their own transactions. Then accounts and addresses are typically grouped into a software that we call a wallet. All right, so when someone tells you Bitcoin wallet, crypto wallet, something like this, they simply refer to a software that contains the private keys and public keys of typically multiple addresses or accounts. All right. Then, why would people even participate in this protocol? I mean, setting up this node takes time. We are all busy. So we want to incentivize people to set up these nodes, download the transactions in blocks, and process the transactions. So each type of blockchain has its own incentive mechanism. Typically, there are two main incentive mechanism or consensus mechanism, like we call. One is called proof of work, which is typically used by Bitcoin, Ethereum, and many others. And another is called proof of stake, which is the one used by our products and also many other products. The idea of proof of work is that whenever you generate a block, we'll give you a present in the form of more tokens, more Bitcoins, right? But if Bitcoins has value, then you always want to generate more and more blocks. So what prevents you from just generating many blocks and flooding the network with blocks and getting a lot of Bitcoin? So we need to make the generation of blocks artificially difficult, and the way we do it is that we define a hash target value that you need to find some kind of string that hashes to a value that is lower than this hash. Okay, and the idea is that this hash becomes higher or lower in order to make the interval of between block generation a constant. Let's say in Bitcoin around 10 minutes. In Ardor it's per 1 minute. So if blocks are generated too quickly, the difficulty will increase, so that the next block will be slower. If the blocks are generated too slow, the network will adjust the difficulty down. So all in all, and all this you have to understand is done without any central coordination. Each node does the same calculation and need to reach the same result. And if it doesn't reach the same result, it should reject whatever it received already. This is called this mechanism is called proof of work, to find this hash that is below some hash. Another alternative is what we call proof of stake. In proof of stake, the idea is that your chance to generate the next block depends on your stake in the network. So if there are billion Ardors in circulation and I have 1 million, so I will generate on average 1 in 1,000 blocks. Okay, but sometimes I will generate twice quickly, sometimes it will take me a while. And again, there is a difficulty adjustment so that the pace of generating the blocks is relatively constant. Okay? Okay, so I know this might be, for some of you, a lot to digest. Others probably know it already, but if you have questions, if someone wants to ask questions at a good time, because I'm going to move to more complex things now. Okay? Yeah. So, just to touch a little bit of use cases. So, of course, transfer value, send Bitcoin or others between addresses. But now think about it. We have these decentralized networks that nobody manages. We can use it for other scenarios. For example, we can use it voting in digital voting is a problem because whoever counts the vote has a chance to change the result of the poll with a single SQL statement or something. But now that you have a network that nobody trusts each other, everybody validates what the other does, it's a good, nobody can actually double vote and cheat, or at least not systematically game the system because of this double spend prevention that we manage. Again, if you can register your identity on the blockchain, it no longer, right today, I mean, in most cases, we identify ourselves with our health insurance, and then again with the travel agencies, and again with the government, and so on. If this is registered on the blockchain and everybody can plug into it, you can actually save these silos of data. So this is the kind of idea that that we're talking about when we're talking with about applications for the blockchain. Let me show you for a second. Let me show you how this actually looks. You see, right now. This is the Ardor wallet. So you see, this is here my public address. Okay, derived from my public key. This is my balance. Sorry. And here you can see some transactions that were sent. Let me try to find something interesting. It's mostly all my. So, for example, you can see in this transaction, I sent an account property on a specific account. So, account property is key value associated with an address that I can later use in an application to use use it for decision making. So this is so this is how transactions look. If you look at if you look here, you see actually how the blocks are generated. So you see where now this is the current block number. It doesn't have any transactions. We'll see later blocks with transactions. And you see that blocks are generated every 10 seconds on average. Here you see who generated the block. The incentive in Ardor is just every transaction spends transaction fee, because we don't want people to just flood the network with endless number of transactions, because transactions are costly, they need to propagate throughout the network. These are so these are the block generators, and the rewards are the transaction fees paid by the transactions included in the block. Okay. So this is blocks. You can also see here, you can see here the generator. These are the guys which are about to generate the new block. All right. So we have in Ardor we have pretty good estimate of when the next block is about to be generated. It's not 100% accurate for all kinds of reasons, but you see, there is also, I think, 10-second discrepancy in this view. But you can see who is. You can see that the guys which has a very large stake in the networks are probably the guys that will generate the next block and so on. Okay, another interesting view is the peers. Here you can see my node actually running on my laptop to which other nodes on the network it knows. It's okay for one node not to know all the network. Nodes can come and go as they like. You don't need any permission to join the network. All you need to do is to have, if you want to generate blocks, then you need to have enough stake to get a chance to generate a block.
Why are the block times 8 seconds on this version instead of
10 seconds. We are looking at the Ardor testnet, which has 10 seconds block time. Okay.
Is there any fine or punishment process conflict is determined?
No. If you try to double spend, the only punishment that you will not have any punishment. In fact, the only thing that will happen is that one of your transactions will expire and not happen. I wish we could punish you, but punishment is very difficult to implement in these protocols. Right. You also need to realize that blocks can be generated legally on different nodes, because there are two generators that only has a few milliseconds apart. They both generate blocks without knowing about each other, and these blocks start to propagate. Still, one of them will be added, and one of them will eventually be discarded. Forks can be even of more than one block. There could be forks of several blocks, and when a better fork is found, it will discard, nodes will discard their existing fork and switch to the better fork. So let's go back to the presentation. Okay, So smart contracts, you must have heard about the term smart contract, but what it really means. Now that we can use this network for transfer of value, identity management, voting, and so on, why don't we actually deploy code into this blockchain and execute this code? So smart contracts are really pieces of code stored on the blockchain and executed by nodes. All right. Typically, they're like every other transaction that is submitted to the blockchain. They are digitally signed and timestamped. Okay, so you can know for sure who is the public, what is the public key of whoever submitted the contract and when it was submitted. Typically, smart contracts are triggered by other transactions that send them trigger to run, or in some cases just by receiving a new block, just triggers the contract. There are many different solutions and frameworks, each with its own language, developed with its own toolset and so on. I will, of course, show our own solution, which is called lightweight contract. Right? So what is the idea of lightweight contracts? So what we are saying is that you develop the contract in Java, in your favorite IDE, compiler, debugger, unit test, and so on. When you're ready to deploy to the blockchain, you package it as a jar file and submit it to the blockchain. The blockchain, of course, stores it just as a byte array representing the jar file. Now, the blockchain itself has a custom class loader that know how to take this byte array from the transaction, form again the jar file, then unpack the jar file and load the class files individually into memory. Then the node is ready to actually execute the contract. Now, it's quite possible that one developer will upload a contract to the blockchain and another node will want to run this contract. But then we need to be, contracts are essentially just Java programs. They can do whatever they like. So we need to protect whoever runs them from anything malicious that whoever develops the contract is trying to do. You'll see in the blockchain world that we always worry about the worst case, about how people will misuse this technology to exploit it. So in order to prevent a contract downloaded from the blockchain from actually stealing information from whoever runs it, or just format the disk of whoever runs it, and you can imagine what else, we run the contract in a Java security sandbox, which is essentially very similar to how Java applets used to run when they were still popular. Another very important factor when running contracts is that you actually want to verify that when someone uploads a contract, this contract is based on specific source code. Now, of course, you can download the contract jar file, decompile everything, and examine. Nobody has time for this, all right? But what if you can take piece of source code that the developer give you, download the contract transaction from the blockchain, and then somehow compare that this source code actually, if you compile it, actually generates this jar file, okay? This will give you confidence that the source code that you were provided with, which is simple to review, is actually what is deployed to the blockchain, right? So basically, I'm going to talk a little bit later on how the security sandbox work, about how the verification of contract work, and another interesting solution we have is what we call parameter injection. contracts are much more useful if you can reuse them, all right? I mean, if for every variation, let's say you have a contract that calculates a tax on some transaction, okay? If whenever you need to change the tax percent, you need to redeploy a contract, it's very inefficient. It's much more efficient to be able to change the configuration of the contract in order to adapt it to changing parameters. So we actually have 3 levels of parameters. I'll just touch it briefly and show you in a moment. There are parameters that you can deploy with a contract, okay? Like we call it setup parameters. There are parameters that you can deploy at the node level. This is good for sensitive parameters. Let's say that you want your contract to access some external web service and you need to put the credentials or the API key of this service somewhere, then you don't want to deploy to the blockchain, because one thing I didn't tell you, but you probably realize now, that everything that is deployed to the blockchain is public, okay? And every transaction that anyone ever deployed to the blockchain, anyone can set up what we call a block explorer and just see the information in it. So we never want to deploy credentials to the blockchain. So instead, we can save them on the node that actually runs the contract. Then the third type of parameter is parameters that you send when you trigger the contract, right? Typically, there is a gambling contract that you want to send it, that you want to define some parameters when you trigger it or something like this. I will try to find you examples of how we're using this. So these are parameters. Let's take a look really at a simple code example of how this thing looks. Okay. So basically, when you install the product, when you install Ardor, you get a folder, program files Ardor, that you can just open in IntelliJ. It's just an IntelliJ. The folder itself is already pre-configured as IntelliJ project that looks like this. And under the contracts folder, you have contracts. All right, so let's take a look at a contract. So a contract is a Java class which extends abstract contract, nothing interesting there. Then it overrides a callback. In our case, process transactions. This means that this contract is triggered by a transaction. Okay, it receives as parameters the transaction context, much the same like servlet, do get, do post, get the servlet context as a parameter. So basically, this, you see, this is a Java code deployed to the blockchain, and it needs to use the blockchain. But we don't want it to actually access the blockchain directly, because it will remain in the blockchain while we upgrade the blockchain itself, so the interfaces may change. So the context is like a bridge between the contracts and the services provided by the blockchain, right? Which is guaranteed to have a stable interface. So even if we can deploy the contract now and be sure that in 2 years it will still be operational, even though we now upgraded the 10 versions ahead. Right? So everything we do through the transaction context. So the first thing that the hello world contract does is bring the transaction, an instance of the transaction that triggered it. It then built a JSON object that has attribute text with the value hello plus the sender account of whoever sends the message. And then it sends back a greeting to whoever sends the message. So it creates a transaction of type send message. This is a chain ID. Ardor is a multi-chain architecture. The recipient of this message will be the sender of the transaction that triggers the contract. So this is go back to the contract. The message is going to be the Java object. And then we use a context in order to create the transaction and send it. Let me try to show you how it looks in practice. So you see, I'm now looking at my contract runner account, what we call. You see, we already have the low world contract deployed. Okay. You see that this account is the runner of the contract. We can see that it was how many times it was invoked and all kinds of parameters. We can see which parameters it expects. Actually, this contract does not expect any parameters. It just echoes whatever is being sent to it. And we can see here what validations it performs, which this thing is basically. Let's say that we have a contract runner. I'm sending a message to one entity, but the contract runner is listening on another account. We don't want him to answer messages not directed to it. So we added, if we look back at the code, we added an annotation, validate contract runner is recipient. So this will only execute if the recipient of the message is actually whoever runs the contract. Similarly, validate chain accept equals 2 means that this contract only listens on transactions on chain number 2. Right? So, and there are several other annotations. Now let's let's use another account to send a message to this contract and see that it actually answers. Yeah.
What is the chain number 2?
Ardor is a multi-chain architecture. I'll show you in a second. Right? Just a second. Let me go. You see, this thing that I'm going to copy now, this is called a passphrase. You can think about it as a seed of the account that the private and public key are derived from. Right? So you see, I'm now logged in. So, Susanna, if you look here, you see that Ardor is multi-chain architecture. So we have actually, right now, these are the chains supported. The Ardor parent chain is responsible for the proof of stake consensus mechanism, while the child chains are responsible for the decentralized applications. It's a unique solution that we have to support more than one chain, right? So,
When you deploy a contract, you're deploying all chains?
No, you always deploy a contract. We have one exclusive chain. It's like our chain. It's called Ignis. And you always deploy contract to the Ignis chain. They can execute, they can be triggered by transactions from different chains, but the contracts themselves are stored in the Ignis chain. Okay?
Exclusive, what do you
You
mean?
can only deploy contracts to the Ignis chain. The contracts themselves. The contracts can, metadata is deployed to Ignis. It can act on any other chain, right? Depending on the parameters. So we are now on the Ignis chain. Let's send a message to the account that actually runs the contract. You see, the wallet already understood that this is a account has a contract that is called a low world, all right? And all I need to do is calculate the fee and send the message, right? You see, the transaction started to propagate. Now it's already got a confirmation. Every 10 seconds, get a confirmation. Hopefully, we are going to see the contract now sending back an answer. And actually, it showed up. It will show up in a second. So now you see you it means this account sent to the contract account a message, And now the contract account sent back a message, right? If you want to see what's in the message, we can open it and see that this message was submitted by the low world contract, and the text is a low, and the name of the sender transaction. That's exactly what we put here in this JSON message. Okay, so no smoke and mirrors. Okay, it's like, okay, so basically, you see the process is, I didn't show you yet how I deployed the contract. The contract was already deployed. I triggered it, and it gave me an answer. Okay. Questions so far? Yep. Whoever submits the transaction pays the fee. So the contract account actually pays the fees for the response. No. The account that sent the trigger message paid this fee, and the contract that sends the response paid this fee. You have to understand that our approach is, in many or most contract frameworks, contracts are executed by every node. Okay, and then contract does not submit transactions; they just update their internal state. In Ardor, it works differently. Contracts are executed by specific nodes, and the result of the contract is not state change to the contract itself, but a transaction that still needs to go through all the normal approval of the blockchain. So, I mean, just to touch it a little bit, the trade-offs are that, let's say, in Ethereum contracts, every node has to execute the contract and reach the same result. But this means that contracts need to be executed very carefully, because if they enter an infinite loop, the whole Ethereum network enters an infinite loop. So for this, Ethereum uses gas and measures the execution of transactions of every instruction and reduces the gas and so on. We take another approach. We say contracts are executed only by a single node. This gives us much more flexibility. Even if the contract runs into an infinite loop, it doesn't kill the whole network, it just kills a specific node. We can fix it and redeploy it and run it. It also lets you run in a general JVM instead of running in some specific proprietary JVM for the blockchain. The trade-off is trust. When you deploy a contract to Ethereum, every node, the running is part of the consensus, so all nodes need to reach the same result. In our case, only one node runs it, and you need to trust it to actually do the calculation correctly. But there are ways to mitigate it. You can use multi-signature accounts and several and setup of runner nodes and validator nodes, which are different roles of nodes, so that you don't need to trust a single contract executor. Okay, are you with me yet? Right. So it's a different approach to contract. I'll touch base a little bit of more of these trade-offs. Okay, so we saw code examples, demos. So just let's talk a little bit about the capabilities that this way of running provides us. So state management, as I said, we don't need to store the state in the contract. This is a big advantage, because if your contract stores a state, let's say that your contract represents a token and stores the token balances inside the contract, and you have a bug that requires you to upgrade the contract. Now you also need to migrate the token balances to the new version, because the contract is the token balances. In our case, the contract will just will not store the token balances, but will just submit transactions that will update the token balances in the blockchain itself. Right? So what we say is that our contracts are stateless, and this also makes it very simple to upgrade the contract. Oracle contracts. The idea with Oracle contracts is that you can access external systems. Let's say that you want a contract to make a decision based on the Bitcoin to euro rate. Okay, in traditional contract frameworks, you cannot do that because each node will connect to the service at a different time and might get different rate. So the network will fork if you try to do this. So it's simply disabled. What we do, because we only run it on one node, we can of course connect to the service provider, get the rate, do whatever we like. Someone will need to trust us that we didn't fake this node. Okay. That we didn't fake this data. Same goes for randomness. For many applications of contracts, you need random source. For all simulations and gambling and things that require random data, decentralized random data is very difficult to obtain because all nodes need to somehow generate the same random data. The only source of randomness you have is the blockchain itself, okay? But everything in the blockchain itself is not really random or can be manipulated in some way. So getting random data is quite a difficult problem. We simply circumvent it because we only run it on a single node, so this single node can generate the random data. Okay. Unit tests. For each contract, because contracts are so sensitive, we always want to test them extensively before we actually deploy them to production. And it's much easier to test them not by deploying them to the blockchain, sending them messages and seeing what happens, like I did now, but to actually write the code to test them. So in our case, what we do for every contract we develop, we also develop a unit test, right? So, for example, for my Hello World contract, I also have Hello World test, right? What the Hello World test does is basically it starts from a clean blockchain that has no transactions at all. The first step, it deploys the contract to the blockchain, okay? Then it generates the trigger message, okay? So eventually it calls message trigger contract and sends the message. Then it generates a block. It really follows what the blockchain does, and then after it compose the message, generated the blocks, it actually tests that it received back the message, okay, from the other from the contract value. All right. So this way you can already develop, and you don't need a blockchain in order to run this test. All you need to do is like run it from the. Okay, yes. It's probably, well, I'm not going to try to debug it now, but generally there is also a runner that you get, contract runner suite, that runs all the tests. I hope it will have better outcome. Okay, so basically you develop your contracts, you don't need to deploy them. Whenever you want to test, you just run your unit test and you are sure that your contracts are okay. Of course, you need to cover all the test cases. Okay, so questions so far?
Are there any
So as I said before, first of all, infinite loop is not a disaster. Okay, the worst it can do is get your node into an infinite loop that you'll need to debug and solve. But other than that, all the tools that are available for any Java program are also available for you. If you want specifically to test against infinite loop, find a Java-based tool that scans for infinite loop. It's not a particularly difficult problem. In this case, there is no designated tool to solve it.
I don't mean it's incidental parts, but if I want to deploy something that will make one node just
So the node will run the contract, enter an infinite loop, see that it's in a loop, and not run it anymore. Okay, there is no longer a systematic failure of the whole blockchain network because of this problem.
I'm still trying to understand the trust mechanism. So, for example, if the code runs in one node, if the data is stored in this node, all the data, because the smart contract is stateless, so all the data is stored in this node. The same node that runs the smart contracts has the state. Is it the case?
No. How it works is that the contract is activated, runs, and then it submits a transaction. This transaction goes through the normal validation, and when it's accepted by the blockchain, it updates the state of all nodes, right?
So all nodes have the state.
Or the state is updated directly to the blockchain. It's no longer stored inside the contract. So in both cases, the state is eventually stored in the blockchain, but in the case of our contract, it's not in the context of the contract.
Okay.
It's in the context of the blockchain.
But all nodes have this.
All nodes will eventually process the transactions that a single contract submits.
And do you have a guarantee that the contract is not changing?
I'll talk a little bit about security now, but I think let's see what are the trade-offs. I mean, right now, if you look at Ethereum, for example, all nodes run the contract, but this is clearly not scalable. So the Ethereum engineers try to come with ways to split the network so that not every node needs to run every contract. But we come from a different angle. We say, in the beginning, only one node runs the contract. If you have something very sensitive that needs verification, you can place, for example, the account running the contract under multi-signature, and make sure that another node actually runs the same contract, repeats the calculation, only then performs only then signs it. Or maybe you can set up 2 out of 3 nodes, so we provide all kinds of guarantees. But in the beginning, the simplest configuration is that only one node runs the contract, and you need to trust. How are we doing with time? We have some restrictions, or no? Okay. So now we have this dilemma. Someone gave us the contract. We said, this guy looks suspicious. I don't want to run it. So you ask him to give you the source code. Okay? So now you have the source code, you scan it, looks perfect. But how do you know that the contract stored in the blockchain is actually the contract that was compiled from this source code? So basically what we do, we take the source code that given to us and compile it, package it to a jar file, and we expect to get the exact same jar file. However, this is a bit naive because each Java version compiles different class files, and there are compiler directives that change the debug information in the class file and so on. So what we do we first of all run the Java P utility on the, basically we load the jar file, unpack it, then run the Java P utility on the classes. Typically there is only one class file of the contract inside. We run it on one class file, and from the Java P, if you know, it's like a decompiler, but it only gives you the metadata of the class. From there, it's quite simple to guess what version of compiler was used to compile the class, and which debug information is contained in this class. Then after we figure this out, we invoke automatically the Java command line with the, we cannot of course change the version because we are already running Java, so we can just report if the versions do not match, but to include debug, but we provide the Java command the same flags that will generate the same level of debug information. Right? And this works quite well. So as long as you're with the same Java version, let's say that you're always working with Oracle Java, then figuring out what debug information is contained in a class file and using the same flag in Java actually really produces the same class file. Right? So so basically we provide some automatic process that compiles the source code you got using the same compiler flag used to generate the original jar and compares that you actually got the exact same jar file byte by byte. Yeah, I tried to give you an example how to do it. The example is a bit ugly. Basically what we do, we run contract manager with a verify flag. We give it the hash of the contract and the source code that represents the contract. Okay, and the end result should show you all kind of information, but here it complains that the contract was compiled with Java 8 and you're using Java 11, right? So rerun the verification with Java JRE version 8. Right. So that's the kind of process that you can use for verification. So questions about this process?
When this verification is it's manually, it's automatic process.
It's let's see what is manual and what is automatic. So the contract is already deployed to the blockchain, and this is the hash of the contract. The source code is already provided to you by someone that claims that this is. I mean, if you develop the contract and deployed it, it's not necessary. Okay, this is for scenario when someone else gives you a contract and asks you, and you want to use it. So they gave you the hash of the contract. They gave you the source code, and this utility automatically performs the process that I described.
It's manual process.
No, it's not manual. Let's take a look. So if we go, for example, to the contract manager, no, we need to open. Let me just see. For example, I would open the. You see, until now I worked with a release. Now I actually switched to an IDE. So. Okay, let's. This is a contract manager, and I will look. Let's try to see how the verification works. So the idea with the verification is that you get the hash and the source file as parameters. Okay. First of all, you load the contract data from the blockchain, and what you do now.
I launched the process manually.
Which process?
This process.
This contract manager is launched manually because you do it offline and. All right. Yeah. All right. Let's not get basically what we are doing. We are calling Java P and then calling Java with all kind of command line and parsing and things like that. Um, okay, so let's talk a little bit about sandboxing the contract. So as we said, we have a specific contract running the contract, but we need to protect the contract runner from anything malicious that the contract tries to do. So we use for this specific purpose, we use the Java Security Manager. That you probably, if you got a chance to ever work with Java security, it's something pretty ugly with a policy file and many many checks that if they fail throw exceptions, throw security exception. It's managed by the policy file, but then we took, let's say we took the policy file to some extreme, okay, to actually allow us several levels of trust. Because by default, when we run a contract, we don't let it do anything, okay? It cannot access, it cannot run threads, it cannot open sockets, it cannot, I think we do allow it to connect to a URL connection. This is allowed, and to read file from a temp folder. So that's pretty much what the contract gets by default. But it's quite possible that some contract that you would like the contract to be able to access some local resources, and for this we have the policy file to let you grant permissions. So if we look at I hope I have it open. Yeah. So, so the idea is that you can grant contracts permissions much the same like when you run an Android app, that you grant specific permissions, but we have another level. You can say you can grant permission to a specific contract, or you can grant permission to all contracts deployed by a specific account, okay? And the way we actually do it is by playing with the information in the policy file. For example, to grant more permissions for contracts submitted by an account whose public key is, we actually call it, this is called the protection domain, is just something we invented called untrusted contract code, signed by, specifies the public key of the account that deployed the contract. And in this case, we allow this contract to access the local database of the node, and also to access a sensitive service called get blockchain. So we allow this contract something more if it was deployed, or actually signed by a specific account. Or we can even take it, a little bit more. We can actually specify the transaction principal, which is the actual hash of the contract. So we can also grant specific permission to a specific contract, not just to all contracts for a specific account. So, then the whole mechanism is controlled by the class loader using objects that are called, that I must say that I've never seen a Java program used before. It's called protection domain, which represents all the contracts. Code signers, which represent the account that signed the contract. Code source means, or maybe, you know what, no. Protection domain is the whole thing, all right? Is the whole token. Code signer is the account. Code source means that this is a contract downloaded from the blockchain. And transaction principal we use for the contract hash itself. So now you can give fine-grained permissions per contract deployed, that by default all contract does not have any permission except very specific permissions. This is nothing that was not done before with Java. It's very typical usages of of this type of applications. Questions? No? Okay. Okay, around parameter injection. So for parameter injection, we use a design pattern called the dynamic proxy that I will try to show you using the example. Let's find an interesting contract. So, you see, for example, this contract, child to parent exchange, it actually solves the limitations that we have in the platform. That hello. Hello. Okay. So the idea we have a limitation in the product that we have multiple chains and we have a decentralized coin exchange running on the blockchain. If you have a child chain token and you want to exchange it into a parent chain token, you have a problem because we do not allow you to do it. Oops, turn this again. I think it's there now.
No, for sure. You can try to the other one.
Okay.
It's about the minor one.
Yes. So, hello. Okay. So we have a kind of chicken and egg problem. You cannot exchange from a child chain token to the parent chain token without actually having parent chain token before to pay the transaction fee. Okay. So instead, we provide this contract that instead of actually using the coin exchange that won't work for you, you will simply send to some address your child chain token, and this address will send you back the parent chain token. So we have a parameter that limits the amount. We don't want people to just misuse the service. We just want it to do for some bootstrapping of the chain. So if you look at how max amount is used, okay, you can see that the max amount defaults to 50, okay? But you can specify when you wait, and one more thing, and it's annotated with contract setup parameter. So I think I'm going to tell it. You see, it's a contract setup parameter. So when you deploy this contract, you set actually what is the maximum amount that you want to allow, and this will override this 50. If you don't specify it, then the value will be 50. The way it works is that when the contract runs, it actually uses the context get params, and then it sends it the params class from above, and then using this magic, it actually extracts the actual value from the transaction, overriding this default value from the interface. So it just lets you more flexibility with specifying parameters to contracts. Okay, let me try. Let's try to let's try to modify our hello world contract. Actually, now I'm so instead of hello, let's say hello to. Okay. Let's see. Now I want to redeploy the contract. Okay, so I can redeploy the contract from the command line. Okay, using the contract manager utilities that I showed you before. But there is a, if you don't want to leave the IDE, then you can go to the. We have a plugin for IntelliJ, right? So you can create another launcher, Ardor. Contract type Ardor contract manager, call it, give it some name, select the class that you want to deploy, hello world, and basically that's it. Now you save it. Let's compile. Okay, so. And let's deploy the new contract to the blockchain. You see the contract runner utility, what it did, you can see it actually deploys 2 transactions and waits for a block and then terminates. If we look at the blockchain, I'll switch back to the contract runner account. You now see 2 new transactions. Okay. The first transaction is upload data. This is actually the contract code itself. So you see it's the lower class, that's the size, that's the MIME type. You can even download it from here. It's on the blockchain. You can download it from here. And we also deploy another transaction type, which is called a contract reference. So we actually separate the actual contract code stored in the blockchain from the contract invocation, right? Why is it a good thing? Because later, let's say that I deployed a contract and I want multiple contract runners to use it, but with different parameters. Then the same uploaded contract can have different accounts that invoke it with different parameters, for example, so that you don't need to redeploy the contract all the time if you just want to change the contract parameters. Let's just to let's see that indeed the message was changed. If I did everything correctly, I'm not sure I did, but let's send again message to the contract account, hello world, and now I need to type the pass phrase, which I have somewhere here. Okay, so again, we trigger the contract. We are now waiting for a block. You see the transaction is still propagated. Nobody created a block. Hopefully, usually in 10 seconds, we hopefully won't wait a lot. Actually, oh, okay. It looks like we got a block, and hopefully we'll get back the response soon. So you can see here the response also is supposed to come with the next block because the contract runner spawns another transaction. You can look. Sometimes you see we probably have to wait something like 20 seconds now for the transaction because this is a long block. Right? let's take a look. Yes, we received a message. So let's go back to the dashboard. And you see I got a message back. And if I'm looking at the message, I can see it's now hello. Right? So I just upgraded my contract and use modified contract. Okay, what more questions?
This moment, there are two versions of the contract.
Correct.
What does prevent the people use the old version start using the new one?
Good question. So you use the contract version that your reference points to. So what this means, let's say that we now have a contract deployed and 3 different account references. Now there is one account experience a problem and want to change a contract. When we deploy the new contract, until we update the contract reference, all contract runners will continue to use the old contract. So this provides us a way to gradually upgrade the contract. So only when you set in order to upgrade the contract, you need to both upload the new contract and change the existing account reference. So accounts that did not change the reference will still use the old version, which is supported and on purpose. Okay.
If I send contract, a message to contract, maybe something, and get the response, the account now send the response, which account is not mine, the receive account.
Right, I'll explain. So the question is, which account actually submits the transaction from the contract? So the idea is that the contract now runner node has a configuration file. Okay, contracts JSON, and this configuration file specifies the secret phrase of the account that submits transactions from the contract.
That account is paying.
Yes. Whoever runs the contract is paying the transaction fees. Yes. In fact, we have in Ardor there is a separate mechanism that we call it a sponsored transaction fees. When you run, as long as you work on the child chains, which runs decentralized applications, and as long as someone is willing to sponsor your transaction fees, you can send transaction without paying any transaction fee. Like if I'm going to the wallet, and you see I'm looking for, just let me fix this password. Okay, wait. Let's see. Let's just make sure I didn't mistype it. No. So let me try. No, I need to set this up. I didn't plan to show it, but you can set up an entity called bundler. Okay, what the bundler does, it takes multiple child chain transactions and packages them into the parent chain. If this bundler is accepting transactions that did not pay any transaction fee, then the end user can submit transaction with 0 fee, and it will be included in the parent chain.
I understand the part of the sender. I as a sender of a transaction, I pay half a little fee, but the account that sent me the response, what motivation has?
His motivation is to provide a service, to run the contract. Let's take, for example, some simple bundling, gambling contract. Right? So okay, this contract, what it does, it is you send this contract some Ignis, okay, and it using random data, it sends you back between 0 to twice the amount that you sent, minus the transaction fee. So this contract finance actually. The user is actually paying the transaction fee for the contract. That's for example.
I pay also for the response, but
you pay indirectly for the response. So this is a type of idea that you can use. Anything else? Right. So. You want me to try to show you the zero fee transactions? Good. I probably need to connect to my online node. Hopefully this will work. This is the same client, but now it's deployed to some. This is the same client, but now deployed to some node in the cloud. So you see that it takes a bit of time to load.
Mientras tanto, habéis preguntado la camiseta. ¿La L te va bien? Así sí que tiene un poco grande.
All right. So now I can show you. You see, right now we have only one bundle, right? For the bundle is for the Ignis chain. It will pay up to 1,400 and something fees in the parent chain, and the rate is 0.5, which means it will accept any transaction. Now, this is starts to get a bit complex, but this defines the exchange rate between the child chain and the parent chain. Now, what I will be very generous, and I will start a transaction that is willing to bundle up to 1,000 Ardor at binding rate 0, okay? And let's use this, no, I can't use this account actually, I need to use the same account that I use for login, so this one. Okay, so now I have a bundler that accepts any transaction. First, let's see that it actually works from this node. So now I'm sending Ignis to myself. Let's say I'm sending 5 Ignis. I'm specifying fee specifically as 0, so it will not calculate it differently. And I'm signing the transaction. Okay, so hopefully this transaction. Let's take a look here. All right, so I just sent a 0 fee transaction. Let's also try to do it from this node. Now I'm doing the same for my local node. So I'm sending, I'm picking some account in general, in random, I'm sending a bit of fonts without paying any fee. Because, and this is very important that I can send a transaction without fee. Because let's say I want to use a blockchain for voting or for identity. I don't want to deal with these currencies. I don't want to exchange them on exchanges and deal with the tax implications and so on. I just want to use the application. So it's very important that the end user will not pay the fee, but that someone will sponsor this transaction fee. Okay, so just okay. Let's let's do some more interesting transaction. Okay, let's set account property. Right, I'm going to set account property. I don't want to trigger. Oops, that is named key1 with a value 1. I want to not pay any fee. And I want to set phrase. This bank account. Yes. And if I look at the dashboard, you can see that this transaction is now confirmed without paying any transaction fee. And if I look at my bundler, where is my bundler? I think I used online. So if I look at my bundler, you see that my bundler actually paid the fee for the transaction in the parent chain. Right, so. Okay, guys, thank you very much.
¿Quiere más camisetas? Vamos a quedar más.
Are there any technical requirements from node blockchain?
It depends. Our solutions are what we call permissionless. Anyone can download the Ardor software from our website and start a node. Okay? If you then you somehow need to get tokens, all right? In order to, if you just want to run the testnet and develop, you just contact us. We give you testnet tokens because they have no value. If you want real tokens, then you need to buy them on some crypto exchange. If you want to generate blocks, you need at least 1,000 Ardor in order to be able to participate in the proof of stake process. But if you don't have something like 100,000 Ardor, your chance of generating any block is very, very small. So there is no real point to. In general, today the gains are not very high. To encourage people to actually generate blocks, what we call to forge blocks, we actually give additional compensation to blocks generator. We have a contract that wakes up every 10 blocks, select one of the block generators in random, and send it a reward to give people more incentive to run nodes and generate blocks.
Create new child chains, like every node can create new child chains?
The way it works is that inside the child chain, we have a lot of functionality. For example, Ignis, you can buy Ignis token and then use all the functions that we have here, like voting and assets and marketplace and so on. But child chain is something we do not let anyone do not let you create by yourself. The reason is, we are blockchain veterans. We know what happens when you give people the ability to create anonymously all kind of entities. It's used too much for scamming and or just toy projects that mean nothing to the author and so on. So with child chains, we decided, even though technically it could be possible to let you to do a creation process of child chains, for now, Jelurida itself controls who creates a child chain, and it's done using agreement with Jelurida. Okay. So to create a new child chain in Ardor, you need agreement with Jelurida. Okay.
You say that you can use Ardor to voting, and you say that you can verify that no one votes each time.
how do you know, how do you limit the people that can vote in this, the people that can vote?
Okay, so voting. First of all, we don't have here robust voting solutions that you can use for Catalonia. Okay, like we're not there yet. We have kind of a demonstration how one can vote. So the idea is that anyone can create a poll, right? Like I'll create a poll. I don't know. You have a lot of options for how to vote, but let's say that you have one vote per account, okay? And we have you can have two answers, yes and no. That you need to choose one, and that's it.
So in that case, people that have a lot of English, this the scoring in the platform, can vote a lot of times. Or
Just a second. No. Yes. In this model, because it's per account, if you have a lot of Ignis, you can just move them to many new accounts and vote many times. Okay. So a better idea is to do vote by balance. Okay. And then it doesn't help you that you split your balance. You still to multiple accounts. You still have the same balance. Okay. So this is also supported, and there are quite a few other modes supported. The limitation here is that every vote is public. Okay, so if I vote now, like I'm going to vote yes. Right? So I just casted my vote. You will see that even though the poll is not over, you already see that someone voted. So for general elections, it's not that good. More robust frameworks actually use encrypt the votes and use all kind of encryption mechanism to actually do the counting without actually revealing the state of the vote before the poll is over. It's possible. It could be something we will develop in the future if someone will want. There are many frameworks for this.